So where's Allison, Sama? Who else is gone?
Noah.
Noah, where are they?
He's probably on
Are they harvesting corn?
Oh, yeah.
Deer hunting. Yes, deer hunting. Well, if you're sitting in a stand, they can't start shooting today, can they?
Oh.
No, they're probably listening to this live as they're walking through the woods. Okay, so back to Usab. What's the purpose of F? No. Just F itself. If I give you F, F is going to increase and decrease because you're computing what when you put an input in? No. The only purpose that F has, right, you have ordered pairs, correct? So when you plug in X, you will always get a Y. So its whole purpose is to find Y. Right? And because it finds different Y's, then it's going to rise and fall. Would you agree? Okay, Adam, what's the purpose of F prime? If F is to find Y, what is F prime trying to find? Slope. Or find where F increases or F decreases. Would you agree? Okay, if it's positive, F is increasing. If it's negative, F is decreasing. Right? Well, now we're going to look at the second derivative. Its purpose is to find concavity. Here's a line. It has 0 concavity. If I take that line and bend it up, it is concave up. If I bend it, it is concave down. All right? So when we have a concavity of 0, that means we have a line. And if you think about it, if I have a line, its first derivative is the slope of that line, correct? Its second derivative, since the first derivative is a constant, the second derivative is 0, right? Because there's no bendiness to a line. It's rigid. All right, so this part right here is just the first derivative test. Examine the function f, and it's to determine whether f is increasing or decreasing. Or define relative extrema, correct? Whether it's a relative min or relative max, right? All right, so the first thing we do is we find the first derivative. The second thing we do is we find the critical numbers, which are x values. How do we do that? It's when the derivative is equal to 0 or when the derivative does not exist. Addison, how is it possible for the derivative not to exist? What does that mean? Okay, so when we take the derivative, okay, and we happen to get a derivative in which x exists in the numerator and then the denominator. Okay? Would you say it again? Right, when the bottom of the denominator equals 0. So we got to examine both places. That's what I'm trying to say here. Very good. Okay, and then we set the intervals with the critical numbers, right? That's what we did yesterday in that little rectangle. and we put a test value into that, that's when Josh said, well, how do we know? Well, because these are our only critical numbers. I don't have to worry about any other. So if I'm in this interval and I get a plus sign, I know that function's going up in that interval. And I pick an easy one. Does that make sense? Alrighty. If the derivative is positive, f is increasing. If the derivative is negative, f is decreasing. Correct? We're all okay with that, right? And then says conclusions about the relative maximum for f can be made from here. We say f is either increasing or decreasing because f prime is positive or f prime is negative. So what I'm trying to do is that these go together. That's what I'm trying to do there on the interval. So here's our statement. So when it asks you to justify, that's the sentence you're going to give. Are we okay with that? Then it says C, f of C is a relative maximum or minimum because f or f prime. If it's f changes from increasing to decreasing. If it's a minimum, it goes from decreasing to increasing. If it's the derivative, you can go from positive to negative. If it's a minimum, it's going from negative to positive. Does that make sense? So these two have to deal with f. And the other two have to deal with the derivative. This is new. So here's figure 1, smiley face. This is concave up. Are you okay with my... And I think Morgan would totally understand why I write CCU, because if I write more than that, it just looks awful, right? Bryn, here's a tangent line. Make up a number for that tangent line. What numerical value would you give it?
Wait, what do you mean?
Okay, you see this right here? You see this tangent line here?
Yeah.
What do you think its slope is?
2.
What?
2.
Can't be. It's impossible.
-2.
Okay, I'll take that. What's this one?
Negative 1.5.
What?
Negative 1.5.
I heard negative and then I heard 0.5. Is there a number that comes before 0.5?
It doesn't matter. 1.
1. It could not be a negative 3. Would you agree? Why? Why can't it be? I agree with you what you're saying. Why?
Because it's not as curved or steep.
Yeah, it's not as steep, is it?
Yeah.
Okay. You're doing wonderful, by the way. What about this one right here? What do you think that is?
0.
0. What about this one right here?
1.5.
Oh, you're going to go 1.5. Okay, what about this one up here?
3.
3. So your numbers are negative 2, the negative 1.5, 0, 1.5, 3. Now you might pick different numbers, but would these numbers be going up? So in other words, the slope of the tangent lines are increasing, correct? The slope of the tangent lines are increasing. Which means f prime is going up. This is the shortcut of this. Would you agree with this? When I write f prime, I'm talking about the slope of the tangent lines. That's why I've been so nuts always saying that, correct? The derivative is increasing. I can say that too, can't I? Now, let's go back to here. When I had f, and f is going up, that means f prime was positive, right? Well, what if f prime is going up? What do you think it means about its derivative? Right? Because that's what the second derivative means. It's the derivative of the first derivative. Yes, sir. It's positive. So this means here that f double prime, the second derivative, is positive. So if I want to look at whether a function is concave up, I can look at the second derivative, and if it's positive in that interval, hello. Yes, he is. Yep. Right. Nick, you're here, right? Yeah. Okay. I told him. Okay. So so if I knew what interval, if the second derivative is positive within an interval, it's concave up. Correct? Now, if I'm concave up, this point right here has to exist. If I'm concave up, this point here has to exist. What is this point? Why is it special? Slope is 0. What? The slope of the tangent line is 0, correct? Making that a what? It's a critical number. On what? It's a critical, I'm going to write this down. This right here is a critical number of f, because this is f right here. That is a what? What are you guaranteed that is? It has to be. It has to be what kind? A relative minimum, right? So I'm going to come down here. It says, as we move from left to right, what is happening to the numerical value of slopes of our tangent lines? F prime is increasing. That means f double prime is 0. That means f is concave up. So let's look at a sad face. Sophia, you see this tangent line right here? Give me a numerical number that could represent its slope. What? 2. Do you see this one right here? Give me a numerical value for that one. 1. This one right here. What would that be? 0. What about this one right here? You think that's a -1? This one here was 1. I'd go with -2. What about this one right here? -3. So you gave me 2, 1, 0, -2, -3. So the slopes of tangent line are what in this case? Decreasing. So that means f prime is going down. That means f double prime would have to be what, Morgan? Less than 0. And this is concave down. Morgan, I'll get this so you can see. Or you get caught up because I don't want to go too fast and interrupt your writing all the time. You see this point right here?
Yep.
I have a slope of 0, which is what Sophia said, which is correct. What can you tell me about that point?
It's going to be critical of F, that's a relative max.
Okay, critical number of F that is you said relative max?
Yeah.
And I think I forgot the word F here. So now it looks like off. That's stupid. So if I would summarize, the first derivative is decreasing. F double prime is negative. F is concave down. All right? So now we're going to have the second derivative test. And I got a couple of things. These are 2 important points. If tangent lines are above F, so here's F. It's above it, isn't it? Would you agree? That's going to be a big idea in a little bit. So right here, this is, let me draw this right here. This is A. This value here is A comma F of A. And this value right here, it's a tangent line, right? So I'm going to call it T. This is A comma T of A. Does that picture make sense? Savannah, here's my question. Which is bigger, T of A or F of A? T of A is, right? T of A is greater than F of A since F is concave down. Well, let's say I have this. Let's say I have this graph. Here's F. This is concave up. I probably should write concave down here. Here's my tangent line. Glances right off the curve. Here's A. Here's T of A. Right here is F of A. Becca, which is bigger now?
F of A.
Yeah, F of A is bigger than T of A since f is concave up. Because the tangent line's got to be below if it's concave up, correct? So it's got to be underneath, doesn't it? Number 2. So this all deals with number 1. Number 2, if the slopes of the tangent lines are decreasing on the interval, the second derivative is negative. If the first derivative is decreasing, f of x is concave down. If the slopes of the tangent lines are increasing, the second derivative is positive, f prime is increasing, and f is concave up. So it's in words what I wrote on the previous page, right? That's all it is. My attempt at English. You can see how on the previous page, right in the symbols, there's a lot less room for me. Here is what's called the second derivative test. To determine if the first derivative is increasing or decreasing, correct? That's one of the things. Or whether f is concave up or down. These are the steps. We find the second derivative. We set the second derivative equal to 0 to find x values that make the second derivative 0. Doesn't this sound like something we've done before? And we're going to find critical numbers. But they're not critical numbers of f. They're critical numbers of the first derivative of f prime. Yes, ma'am.
For number 2, where it says the second derivative of f equals 0, but it also says the first.
Yeah, it should be second derivative does not exist. I'm glad you caught that, because again, it's the same type of rule. Those critical numbers can be in the numerator or the denominator. Just like Abby said, they could be on the top or they could be on the bottom. Okay? Now here's the thing. Do you guys know what I mean by first generation, second generation, third generation? Okay? My dad's first generation. I'm second generation. My son Sam is third generation. Does that make sense? My dad is my father. I am Sam's father. So if my dad's the function, I'm the first derivative. My derivative is Sam. Or he's the second derivative of my dad. Does that make sense? These functions are kind of the same thing. In other words, when I take a derivative, set it equal to 0, I'm determining the critical numbers of the generation before it. Does that make sense? So when I find the second derivative and set it equal to 0 and come up with those x values, I'm finding the critical numbers of the generation before it, which is the first derivative. Does that make sense? It has impact on that function, but the critical numbers are of the first derivative because it only goes one generation back. Are you okay with my analogy? Okay. That's why it's these. Now, we have these critical numbers are possible inflection points of f. What are inflection points? Let me show you. And I'm going to show you by using this curve. This is a very common curve we like to use in math. It's one of my favorite curves. It's the sine curve. This interval, here's from 0, here's pi, here's 2 pi. You saw that last year, right? This has a maximum here, pi over 2. Right here's my maximum number. It's pi over 2 comma 1, right? Notice it's in a concave, it's concave down, isn't it? And then it changes to concave up. At x equals pi, it changes from concave down to concave up. X equals pi gives me an inflection point. Because concavity changed. It went from concave down to concave up at pi. At pi. It changed from concave down to concave up. I will show you why that is using calculus. But can you see the picture that it changed? So in other words, there's a tangent line right here. And then all of a sudden it switches to this side, doesn't it? Right? It goes from being above to being below at that point of inflection. All right? So, we create intervals with the critical numbers. We check a test value in the second derivative. If the second derivative is positive, it means the first derivative is increasing and f is concave up. If the second derivative is negative, the first derivative is decreasing and f is concave down. So you can make conclusions about the concavity of f can be made. Hey, it's concave up in these intervals. You also can make conclusions about the relative min and maxes. Allison, who is gone, brought that up. Allison! Okay? And I'm going to get to that in a little bit. That's an important thing to remember. You may want to star that because you may see that on Tuesday's quiz. All right, here we go. Determine the open intervals on which f of x equals x cubed plus 2x squared is concave up or down and find inflection points. So the first thing I have to do, Ethan, is find the first derivative because you can't find the second derivative unless you find the first derivative, correct? It's not like you get grandchildren without having children. I guarantee you, even when you have children, you don't get grandchildren. Ask my wife. It's driving her nuts. Okay? She cries every time her sisters become grandparents again. So, what is f prime of x?
3x squared plus 4x.
And so what is the second derivative?
6x plus 4.
Why did I write 3? I have no idea. Okay? I'm going to set that equal to 0, and you're going to solve. What is x equal to?
2/3.
I get a negative 2/3. Does that look right? Okay. So, because I have one critical number on the derivative, and you take a look at this derivative is a parabola, right? A parabola only has one critical number, correct? And, Lillian, this is a parabola that goes up. Do you know why I know it goes up? Because a is positive. So this has to be a minimum of this parabola. Okay, now, because I have 1, that means I'm going to have 2 intervals. I'm going to go from negative infinity to a negative 2/3, and from a negative 2/3 to a positive infinity. Madeline, does that make sense with what we've done before? Okay? So now you're going to give me a test value and be nice to me. What number, easy number, exists from negative 2/3 to negative infinity? So to the left of a negative 2/3 on the number line. Beautiful. That was what I was hoping you would say. Okay? So what number over here would work that's nice, that's to the right of a negative 2/3? There's even one better than that, 0. Okay. You could choose 1, but 0's a lot easier than 1 because sometimes when I take 6 times 1, I get 7. And it won't make, in this case, it's not going to be a big deal because I'll still get a positive answer. But when I multiply by 0, it's a lot easier. Okay? So now, if I put a negative 1 into the second derivative, do you see that it's negative, folks? Right? Because I get a negative 2, but I don't know. I can see a negative 6 is more negative than 4 is, so it's negative. And when I put 0 in there, I get a positive. Well, what does that mean? Well, that means f is concave down, and it means that the derivative is decreasing. It means the derivative has got to be going down. And it means my function's got to be concave down. What does this mean? It means my function's got to be concave up. And it means my first derivative has got to be increasing. And what's happening at x equals a negative 2/3? What's happening there? My function goes from concave down and then switches at x equals a negative 2/3 to concave up. What does it have to be? It's got to be an inflection point. It's not a relative minimum or maximum of f. It's an inflection point of f. So I'm going to write a few things here. I'm going to say f is concave down on negative infinity to a negative 2/3 since f double prime is less than 0 on that interval. F is concave up on negative 2/3 to positive infinity since the second derivative is positive on that interval. Austin, I need the inflection point. I know that x equals a negative 2/3, correct? Where do I get, but I need the point to look like this, right?
Can I have your attention, please? As we plan for our Veterans Day program, we ask that any students who have enlisted in military services report to the office at the beginning of connection today. Again, any students who have enlisted in military services, please report to the office at the beginning of connection today. Thank you.
Anybody in here?
Is that today?
No, it's the 11th is Monday. They're just getting ready for Monday. Okay. So what do we, Austin? What do I need? I need a y. Where do I see? You see how I always ask, almost at the beginning of class, there are certain things that give us y, certain things that give us slope, certain things that give us concavity, right? Where do we find y?
X into F.
Plug x into f. So I'm going to have to put a negative 2/3 into, what is f? Oh, a negative 2/3 cubed plus plus 2 times a negative 2/3 squared. See you Monday. We'll finish up Monday and you'll have some work time.